Today we're going to talk about the idea of antiderivatives, which are basically the opposite of derivatives. And so I'm going to start by just doing some examples. If we want to find an antiderivative, we're basically trying to figure out what function has the following derivatives. So we're given the derivative, we're working backwards. And so we're going to try to find one possible antiderivative of each function. And in these first examples, I'm just going to do this based on my knowledge of derivatives. So what function has a derivative that is 2x? The answer is x squared. X squared is an antiderivative of 2x. What function has a derivative of e to the x? E to the x is an antiderivative of e to the x. What function has a derivative of 3x squared? Well, x cubed has a derivative of 3x squared. And then finally, what function has a derivative of 5? That would have to be 5x. Now, in these problems, I just listed one antiderivative of each of these functions. However, every function has more than one antiderivative. So, for example, if we take a closer look at part A, f of x equals 2x, I said x squared is an antiderivative. But another possible answer would have been x squared plus 6. X squared plus 6 has a derivative of 2x. And in fact, I could have added any constant, and I'd still get the exact same derivative. So if we're asked to find all antiderivatives, which is typically going to be the case, we are going to indicate that by saying, well, our antiderivative is x squared, and then we're going to tack on a plus c to indicate that we could add any constant, and we would still get the exact same derivative. Now, antiderivatives are also called indefinite integrals, and so I've got listed in the box below the notation we're going to use when we're trying to find antiderivatives. So, for example, that previous problem that we just did, find all antiderivatives of 2x, I would write that with this integral symbol, and then I would put a 2x there, and then I put this little dx. We'll talk more about that in a future section. But the dx is just part of the notation. It basically tells me what the variable is. So this symbol means find all antiderivatives of 2x, and we learned that the answer is x squared plus any constant. Now, just like we had lots of derivative rules, we are going to learn lots of antiderivative rules. And so I'll just run through this list real quick, and then we'll do some practice. My first rule says, as long as your exponent is at -1, if you want to integrate x to a power, so say x to the third, what you have to do is you add 1 to the exponent, so that would become x to the fourth, and then you divide by 4 and tack on your plus c. So x to the fourth divided by 4 has a derivative of x to the third. My second rule says if I have a constant times a function, so for example, if I have 5x to the third and I want to integrate it, I can actually just pull that 5 out front and integrate the x to the third, and I would get 5 times my x to the fourth over 4 plus c. So if you have constant times a function, you can take the constant times the antiderivative. The third rule says if you have a sum or a difference, you can integrate each piece separately. Number 4, the antiderivative of e to the x is e to the x. And then I'll show you an example of number 5. If you have, say, e to the 2x, that's something of the form e to the kx, you'll always get 1 over 2 e to the 2x plus c. So if there's a constant in front of that x, you have to divide by the 2. It's basically your chain rule backwards. If I have, say, antiderivative of 3 to the x, this rule is saying you take 1 over ln 3 times 3 to the x plus c. Rule number 7 would work for something like integrating 5 to the 3x. This rule says the answer would be 1 over 3 ln 5 to the 3x plus c. And finally, the last rule says when you integrate 1 over x, you get natural log of x. All right, so let's do some practice. First thing I'm going to do is change that square root of x to an x to the 1/2. I have a difference, and so I can actually integrate each piece separately. I can integrate the 5x to the 1/2, and then I can integrate the 1 over x. The 5 is a constant. I can pull that out front. and really just integrate the x to the 1/2, and then integrate the 1 over x, and the difference of those things will be my answer. Now, you don't have to write out all these steps if you don't want to. I usually don't write out all the steps like this, but I want to show you a lot of detail for this first example. So then using my rules, the 5 stays there, so I've got the 5. X to the 1/2, let's see, I add 1, I get x to the 3/2, and then I have to divide by 3/2, and we'll simplify that in a minute, minus, and the antiderivative of 1 over x is natural log of absolute value of x. And then we always put a plus c in there. Now, dividing by a fraction is the same thing as multiplying by its reciprocal. Copy, dot, flip. So dividing by 3/2 is the same thing as multiplying by 2/3. And so my final answer is going to be 10/3 x to the 3/2 minus natural log of x plus c. Don't forget that plus c. All right, example B, we want to integrate x minus 4 squared. Now, there actually isn't a product rule or a quotient rule for antiderivatives. And so what I'm going to do to integrate this is I'm going to expand this, and then I'll have a sum and a difference, and I can integrate each piece of a sum and a difference separately. So x minus 4 times x minus 4 would be x squared minus 8x plus 16. Now that I have sums and differences, I can integrate each piece separately. And this time I'm not going to write out quite as many steps. So I'm going to just integrate each piece separately though. If I integrate x squared, that would be x to the 3rd over 3 minus the 8 stays there. That's an x to the 1. So I add 1, I get x squared over 2. And then to integrate 16, I would get 16x. And then plus c. So this I'm going to write as x to the 3rd over 3 minus 4x squared plus 16x plus c. All right, example C. Let's do the same kind of thing. Let's see, the 5 stays there. X to the 7th becomes an x to the 8th over 8 minus, that 7 is a constant, so I'm just going to write down the 7. And then we're integrating a 1 over x. That's going to give me natural log of absolute value of x. So again, with that term, what I was really doing is pulling the negative 7 out front so that I would have a 1 over x. Okay, last term, e to the 2x is going to become a 1/2 e to the 2x, and then plus c. There's nothing else I can do with that. That's my final answer. Part D, let's see, we have a quotient. There is no quotient rule for antiderivatives. There is no quotient rule for antiderivatives. And so we actually have to do this division before we can integrate. This is the same thing as 7x over x squared minus x to the 4th over x squared dx, or 7 over x minus x squared dx. Now that I have a difference, I can integrate each piece separately. The 7 is a constant, so I would get a 7. And then you have a 1 over x, which becomes natural log of absolute value of x. And if you integrate an x squared, that's x to the 3rd over 3. And then, of course, always put those plus c's in. All right, let's do a couple applications of finding antiderivatives. So in example 4, we are given the marginal cost. So we're given a derivative. We want to find the original, the starting cost function. If I am given a derivative and I want to find the original function, I can integrate or find the antiderivative. So I'm going to integrate the 5x minus 0.2 x squared. That would be 5x squared over 2 minus 0.2 x to the 3rd over 3. And then, of course, I would need that plus c. Now, in these application problems, we can actually figure out what the plus c is. They're telling us if we have 8 units, so if x is 8, the cost is 10. And so I'm going to plug 10 in for cost, and I'm going to plug 8 in for x. And this is going to allow me to actually solve for c. So let's see, that would be 10 equals 160 minus, I think that was 34.13 plus c. So if I just get the c by itself, I got c equals 115.87. And so my final answer here, my cost function would be 5x squared over 2 minus 0.2 x cubed over 3. And then now I know that constant, plus 115.87. So it's the same idea as before. The only difference is we were given enough information that we could actually figure out what that constant was. My next example involves positions, velocities, and accelerations. And we've learned in the past that velocity is the derivative of position. Acceleration is the second derivative of position. So I guess in the context of antiderivatives, we could say that the velocity is the antiderivative of your acceleration, and your position has to be the antiderivative of your velocity. Okay, so this problem says, here's your acceleration function, a equals negative 32. If an object is thrown upward with an initial velocity of 10, so that's telling me at the starting time of 0, the velocity is 10, and it has an initial height, or an initial position, of 5, we are supposed to find a velocity function for this object. Okay, so we are given the acceleration. To find the velocity in terms of time, I am going to integrate my acceleration, which is negative 32. And because t is my variable, I'm going to integrate with respect to t. So that's why I put that little dt there. It just tells me that t is the variable. So let's see, if I integrate negative 32, I get a negative 32t, and then of course I need that plus a constant. Now, just like in the previous problem, we can actually figure out what that constant is because we were told that the initial velocity, if we plug in 0 for time, the velocity has to equal 10. And so I'm going to do that. I'm going to plug in 0 for time. Velocity is 10, and I can actually solve for c, and I end up getting c equals 10. So my velocity function is negative 32t plus 10. Now in part B, they ask us to find our position function. To find position, we are going to integrate our velocity, again with respect to time. So let's see, that would be negative 32t squared over 2 plus 10t, and then again plus that c. Now once again, we know the initial position. We know that if t is 0, s has to equal 5. If I plug in 5 for the output and 0 for the t's, that'll actually allow me to solve for c. That tells me that the constant actually has to be 5 here. And so my position function is negative 16t squared plus 10t plus 5. So to summarize again, that idea was we integrate acceleration to get velocity. We integrate velocity to get position. And if we're given initial velocities, initial positions, that information actually gives us that constant. Finally, they ask us to do one more thing. When will the object hit the ground? So I'm talking about position. And so they are asking us, when does our position function, our height function, equal 0? So I just set my s equal to 0, solve for t. This is a quadratic equation. I don't think it can be factored, and so I'm going to use the quadratic formula instead. So t would be negative b plus or minus the square root of b squared minus 4 times a times c, all over 2 times a. That becomes negative 10 plus or minus the square root of 420 over negative 32. And I put that into a calculator and got two different solutions, negative 0.33 and 0.95. And if we're talking about times, that negative solution doesn't make any sense. Time can't be negative. And so the answer would be just under 1 second is when the object hits the ground.